Alright, welcome back. We're still looking at heat conduction, heat equation. So far we have looked at a case when we had a rod with ends that were held at 0 degrees, right? Constant 0 degree temperature. And I will tell you exactly why I did that case first before I'm about what I'm about to show you. So for heat conduction, we typically have two solutions, what's called the transient solution and a steady state solution. Basically what we found in the last video was the transient solution when our answer was the transient solution. So the transient solution is the temperature distribution. For this case, the temperature distribution before steady state. So it's basically for all t leading up to the time where steady state's achieved. And then the steady state solution if we're thinking about our example, if we have a 60-degree end on the end of a rod, two 60-degree ends, eventually the entire rod is going to be at a certain temperature somewhere. It's no longer going to change once it hits that constant 60 degrees. Once it's heated up to that point, right? The whole rod will be at a different temperature, but it won't be changing. So in that case, it's when the temperature distribution, when a system equilibrium is reached. And for heat equations, the solution is defined as the steady state solution, you notice independent of time, plus the transient solution, which is dependent on time, because steady state solution is not changing with respect to time once we get to that point. So it's independent of time. So why didn't we have a steady state solution in the last problem, in the last video? Well, for that case, when you have two zero boundary conditions, like let's say we have right? These were like our boundary conditions in the last video. Why do we ignore the steady state solution? Because I knew it was zero. That's why I did that before I did this, because for those problems, you don't have a steady state solution, and I'll prove it to you right now. You kind of think about it intuitively. If the ends are zero, the rod is going to go to zero, which means like the rod eventually, the whole rod is going to be at 0 degrees. Eventually. Which makes sense. Right? How can the rest of the rod be a higher temperature if the whole thing's at 0 degrees? Right? This is assuming like we're in like a vacuum or whatever. Like you don't have any other factors. Like it's not sitting on a table that's a little bit warmer than what's being applied on the ends. Like you're kind of assuming it's in like a vacuum. But see, you can kind of imagine that over time the whole rod will eventually go to 0 in that case. But now if we have something like this, of course the one end would be warmer and that would distribute throughout the rod slightly. So like say at like U1 of T, it might be like 2 degrees, it might be like 8 degrees, and then so on. It'll go to 0 eventually. And that would be steady, but the steady state solution would be non-zero then. Because of this, the steady state solution is going to be 0, and I can show you exactly how we're going to figure that out. So, we know that u of s is not dependent on time, so this is 0. So, we're looking at the heat equation, by the way. Right? So now, but u of s of x is going to just be u of s, and u of s of xx is going to be us double prime. Sorry, us prime. So this can be rewritten, and that just goes away. So then you solve the characteristic equation, and you end up with repeated roots. So then our general solution, u of s, is just this. Then we use our boundary conditions. We get C1 is 0. We use the other boundary condition, and we get C2 is equal to 0, and that tells us that u of s of x is equal to 0. See how that works? That's why I ignored that part of the problem when we did the last example. But from now on, we're going to need to look at it. Because what if we have a problem where one end is a different temperature than the other end? What if they were the same temperature? We can test that out. We'll test it out. We'll do both. Let's do this. Let's do it for this case, and let's also do it for... Let's also do it for that case. Let's see what happens. Let's see if it matters. Let's see if the change in temperature on the ends affects the steady state solution. Let's see how it affects it. So let's do this one first. So this is always going to be the same. We're always going to end up with this, this general solution for all of them. So then we go ahead and use our conditions here. C1 equals 10. C1 is 0 plus C2x. So C2 is equal to, well, oh wait, plus C1, so plus 10. That's 30 over 50, which is 3/5. So then our steady state solution for this case would be 3/5. Right? Let me make sure that's right. I have the solution here. Yep. Now, I made this case up over here. Let's see what kind of answer this gives us. You might have a theory as to what it would be. You can see there's no difference. Think about it this way. There's no difference in the ends of the rods, kind of like this one up here. No difference in the ends. Doesn't matter what temperature it is. You're thinking it's probably 0. Well, you're thinking correctly. C1 is 10. Plus C2x. That's 0 is equal to 50. C2 equals 0. So steady state's, well, it's not 0, it's going to be 10, right? The steady state solution for this one. It stays at that temperature. It moves towards that temperature, right? So you can see how that works. You have this extra bit right here. That's that difference throughout x at that steady state solution. So like, you know what I mean? Like as you move from one end of the rod to the next, it's going to change slightly in x. So that's that change. Let's look at the next one. What if we have a mix between a Newman boundary condition and a Dirichlet, however you say it, boundary condition? Right, this is a Newman, this is a Dirichlet. Newman just basically states that like it's kind of like, think about it as being like insulated, so that end of the rod doesn't have any heat transfer. Nothing's changing, so it's being held constant. This just says that dx dt that dx dt is 0 at that point. There's no change in I'm sorry, no, not dx, du dx is 0. Sorry. But what happens in this case? So we start off with the same general solution. Right? That's C2. So then U of S prime of 0 is equal to C2, which is equal to 0. The other end, C2 is 0, so C1 is equal to 0. So C1 and C2 is 0, so then U of S is 0. So this happens because we have one end that is, now these are different temperatures, okay? This end of the rod, say it's 50 degrees, but it's not changing. There's no heat flux at that end. There's no heat flowing out of the rod. I mean, yeah, there's no heat flowing out of the rod or into the rod at that boundary. So what's happening is the end of the rod that's fixed at 0 is allowing heat to flow out of the rod, while the insulated end prevents heat flux over that boundary. So over time, that heat is going to dissipate through the through this end, right, driving the temperature 0 basically everywhere. Yeah, everywhere. Yeah, if that makes sense. Even if this is at like 50 degrees. You're going to have that very instance of that end that's at 50, and the rest of the rod is going to be at 0 throughout. That's what I'm trying to say, over time. That's how this works. It's an insulated end. It's like separate from the rod, basically. You can think of it that way. It's separate from the rest of the rod. So it's interesting, right? Next case. This is the exact same thing, different ends. We can say the same thing, right? We know that now. We're starting to see the pattern here. We know this. Okay, we have what's called a Robin boundary condition, which is a mix between a Dirichlet and a Newman. And we have a Dirichlet boundary condition. This is an interesting case. So we start off with the same thing again. Right, we're given this case. So we need to find well, they give us this. Writing minus U of 0 is equal to 0. That's what they give us. So this would be C2 is equal to C1. See how I got that? And then let's look at the other boundary condition. Let's plug in for C2. T over 1 plus L, right? So if that's C1, we know that C1 is equal to C2. So let's plug the stuff into here. Right? And then we can rewrite that. That's correct though. This would be of x, of course, not time dependent. Alright, so here would be our steady state solution for this problem. Pretty simple. Pretty simple. See, it's not that hard to do. So that's how you find a steady state solution of the heat distribution. So you can see how this kind of works now. So now in the next video, we're going to have an example where we have a rod whose temperatures differ on the ends. Okay, so temperatures will differ on the ends, so then we're going to have to deal with steady state solution and the transient solution. So in the next video, we're going to look at that. And we're going to solve the full PDE as well. We're going to find U of x of s, okay? So I'll see you for that video.